Okay, make sure your phones are away. So basically when that bell goes that says class starts, your phone needs to go away immediately because we don't have time for anything. So, did you have any difficulties writing the dissociation equations? Or were we good? This was like page 13, 13, 14? Any problems, 13, 14?
No.
Did we check our answers with the answer key?
Yeah.
Did we make sure we wrote our pluses and our minuses?
Yeah.
Did we make sure that we wrote our aqueuses and our solids?
Yeah.
Excellent. I'm so glad to hear it. Now, the other thing I wanted to check on is how did kinetics go, reaction rates? How did we do with that? It was a little bit Okay. So we're going to take a quick look at that one today to make sure that you feel okay about it. All right. So we are on, in your yellow book, on page 1. So this is page 1 of your yellow book. Now, rate. When we're talking about rate in chemistry, we are talking about reaction rates. How fast does a reaction go? And I'm just going to tell you guys right now that this pen drives me crazy because do you see how that go has this stupid little thing down here? I did not draw that. It just does that. And when I was drawing a circle this morning, I drew the circle and it didn't go like that. It went like this. And I'm like, why? So just so you know, when it does weird things like that, I am not doing that. Okay, it's just the pen. And I'm going to try not to comment on it every time, but you might see me go like this. Okay, because it's frustrating. I'm like, why? Why is there this weird thing? Okay. All right. Did we watch the video? How many people watched the video? About half of you. Okay, if you did not watch the video, then you want to think about whether you want to be in Chemistry 12. Yes? Because when I say watch a video, you need to watch it because you need to be ready to go. All right? And it was only a 3-minute video, so, you know, very, very quick. So when we're looking at reaction rate, are you guys familiar with the capital Greek letter delta? Yes, what does it mean? Change in. So we are looking at the change in the amount of either a reactant or a product over the change in time. Is good? Okay. So here we have a reaction. And if we look at our reactants, we have zinc, which is a solid. So maybe it looks like, you know, just a little chunk of zinc. And over time, what is going to happen to that chunk of zinc? It's reacting with some hydrochloric acid, which is aqueous. That means it's dissolved in water. Okay, so we've got our hydrochloric acid here. All right. What's going to happen to the amount of zinc as time goes on? It's going to shrink. Okay, so it's going to get smaller. How could we measure how much smaller it gets? We can look at the change in mass. You could measure the mass at the beginning. You could wait 5 minutes and then measure the mass after 5 minutes. Okay, so that would be saying, what is the change in mass of zinc over the change in time? Okay. Let's take a look at our products, because we could also measure the change in the amount of product over the change in time. And here we have a gas. So in theory, we could collect this gas, okay? I think actually, do I have a picture of how to collect the gas? Give me just a second here. How to measure rates in the lab. I'm just gonna grab this. You don't have to go here. Pressure, oh, here's volume, okay. So here we have perhaps some zinc down in this flask along with some hydrochloric acid. And we have up here a syringe. Yes, this is on page 24 if you're interested in looking. Okay, if you have trouble seeing it up here. And what might happen is over time, we get bubbles coming up. Okay, and what are those bubbles going to do with that syringe? There's a plunger, right? We got the little plunger there. What will happen to the plunger as the gas is produced? It's going to move, right? Because the gas is going to be pushing on it. So the plunger is going to move that way. And what we can do is we can say, oh, here's 1 milliliter. Here's 1, 2, 3, 4, 5 milliliters. And we can measure the volume of the gas. Yeah? So that's one way to measure the volume of a gas. So if you have a reaction where a gas is made, you can measure the change in volume over time. What if you don't make a gas? Can you measure change in volume? Okay, so if you don't have a gas, like solids don't change in volume significantly, liquids don't change in volume. If you've got all aqueous, you're not going to have a significant change in volume. So only if you have a gas can you measure volume. Okay, that's one way of measuring volume. Another way is you get yourself some sort of container and you've got some water in that container. Okay, and you get a tube and you fill the tube up with water. So the tube is initially facing this way and you fill it to the tippy top with some water. Okay, beautiful picture. There's a reason I'm not an art teacher. And then what you do is you put your hand over the mouth of it and you turn it upside down, and then your little bucket of water is here and you turn it upside down and you go, and you put it in and you take your hand away. And now you have a tube that is full of water all the way to the top. And then you have your reaction mixture over here and the bubbles come up. Where do the bubbles go? The bubbles go through the tube. Okay. And what you do is you take the tube, and usually you would have something that's flexible, like, you know, this kind of a thing here, some rubber tubing, okay? And you can feed it up and underneath the tube. So what's going to happen? The little bubbles are going to bubble up through here, and the gas will start to collect up here. And as the gas collects, the water is going to come out and just be displaced into the rest of the bowl. Okay? Pardon me? Am I recording? I am. Thank you for checking, though. I appreciate it. So now we have this thing. It's called a eudiometer, but you would only ever have to call it a gas collection tube. In fact, you wouldn't necessarily even have to call it that. You could use a graduated cylinder for this purpose because a graduated cylinder has markings on it, yeah? And the important thing about this tube is that you need to have markings on it. So this one says 100 milliliters. So you might say, I'm going to start my timer when I put the little tube under there and I press start. and I say, oh, 3 minutes have gone by and I've collected 100 milliliters of gas. So that would be 100 milliliters of gas in 3 minutes. Why did I pick that number? Because it doesn't divide nicely. But anyway, I would have 33.3 milliliters per minute. And that would be my reaction rate. Does that make sense? Okay. So that's gases. So we could do a change in the mass if we have a solid. This is back on page 1. We could do a change in volume as long as we have a gas. Now, does anyone remember what type of a compound HCl is? See if you can tell your partner what type of compound we have when we have HCl. It is covalent. We do have hydrogen, which is a nonmetal, and chlorine, which is a nonmetal, but there's even a more specific category. Acid. Yes. Okay. Whenever you see this H, this is an acid. And I don't know, do you remember from either grade 11 or grade 10, how do you measure the acidity of something? Do you remember the scale that we use? We use the pH scale to measure the acidity. Okay. So the pH scale can measure acidity. All right. And the really nice thing about that is that we actually have a device that will measure the pH for us. And literally, we just have a little beaker and we stick the little probe in the beaker and there will be a little digital readout that says what the pH is. Now, the reason I'm not demonstrating this is because when I say we have things, what I mean is the scientific community. When I say we as a school, we have some ones that haven't worked in about 10 years because that's, you know, the education budget. So I'm not even going to bring them out, but we are going to look at a picture. Is that the one? Nope, that's the one. So we're back here. There we go. On page 20. Page 20. Here we go. 21, sorry. So if we have an acid, we can measure its pH using a pH meter. What are you looking for? Place to sit. Ah, because we're really full. We got a chair right here. Yeah. Yeah, this is my block of 30. So, yeah. So if you have an acid, you can use a pH meter because it measures the acidity. So what does this look like? Well, here's one style. You've got this little probe that goes into the solution. And you can see this one says that the pH is 7. Do you guys know what pH 7 means? That means it is, pH 7 is actually, is it acidic, is it basic, or is it neutral? Do you remember? Neutral. It is neutral. Okay. Don't worry, we have a whole unit on the pH scale. You're not necessarily required to know that right this moment, but I thought I might as well preview it a little bit. What if the pH is less than 7? Do you remember what that means? If the pH is less than 7, are we acidic or are we basic? We're acidic. And if the pH is greater than 7, we are basic. Okay? All right, so that is how we can measure it. Now, acidity is a measure of the H+ ion. Okay? And it is the concentration of the H+ ion. Do you remember a notation that we use to show concentration? Yes, we use those square brackets. Do you remember the square brackets? Square brackets mean concentration of, okay? Now I'd like you to tell your neighbor if you remember what units concentration is usually measured in. See if you can remember that. Anyone remember? Moles per liter. And how do we shorten that if we want to? Capital M, okay? And how do we pronounce capital M? We pronounce it molar, okay? So if we have square brackets, we are talking about the molar concentration specifically. You can measure concentration in grams per liter, or you can do it in, like there's a percent by volume, percent mass by volume. But if you put the square brackets around it, that specifically means molar concentration measured in moles per liter, not in grams per milliliter or anything like that, okay? So if the pH is less than 7, we are acidic, and acidity is caused by the H+ ion. What ion causes something to be basic? See if you can tell your partner, what ion causes something to be basic? It is OH. Now, to be honest, in every solution, no matter if there's H or there's OH, you will actually have both, okay? You will have, but if you've got a basic solution, you have more OH. And if you have an acidic solution, you have more H+. Okay? And how do we know where we're at with our acidity or basicity? We use a pH meter, okay? And it might look like this. The ones that we have, the ones that don't work very well, look like that, okay? And they just register the pH. So here we have a reaction happening here. And if we look in this beaker, we have aluminum foil and we have hydrochloric acid. Yes? So let us, and I know the reaction's right there, but let's see if you know what, if you got something, cover up that reaction and see if you can predict the products. Okay, so cover it up. Get yourself a piece of paper if you don't have one already. And remember, there's free paper at the back there if you need any. Don't be shy. Lots of free paper. Help yourself to as much as you need. I'm always making more. See if you can remember what type of reaction this is. We have an element and we have a compound. That is a single replacement. So then you need to think to yourself, the aluminum is going to replace something. Is the aluminum going to replace the hydrogen or is it going to replace the chlorine? Tell your partner what you think. Is the aluminum going to replace the hydrogen or is it going to replace the chlorine? And this might be helpful if you remember that hydrogen, when it's in a compound, will be plus almost all the time, okay? And chloride is going to be negative, and aluminum is a metal. So when aluminum gains a charge, does aluminum become positive or negative? Metals always become positive. Metals always become positive. What do we call positive ions? Cations. So that means that aluminum is going to replace the hydrogen. Don't be shy about using your pink booklet to predict what the correct formula is for that compound when the aluminum kicks out the hydrogen. And if you're stuck, there's a couple of things you can do. Number one, you can look in here. In grade 12, for whatever reason, they feel like they need to give you all of the charges. So you can be like, oh, aluminum starts with A. So I can look under A on page 3, and it tells me that aluminum is 3+. Now, if you want to be quicker about it, because you're like, I don't want to always be flipping to page 3, I would just like to use my periodic table. Let's go back to our periodic table. Remembering the charges based on the periodic table is as easy as 1, 2, 3. Ooh. So, if you had to guess what charge ions group 1 forms, what would you guess? Group 1 forms charge plus 1. Now, when you write your test, are you going to have this on your periodic table? No. Okay, so it would behoove you to stick it in your brain, but also you don't really have to, because remember, you've got your common ions here, and you can look up that calcium, which is in group 2, has a 2+ charge. Okay, but it is really nice to just be able to look at your periodic table and go, oh, there's calcium. Is it in group 2? So it is +2. Now, group 3 is actually plus 3. And then we're going to skip them. Why are we skipping all in the middle? They are transition metals and they have variable charges, yes? Okay, and if you look on your table of common ions, for example, under I for iron, we have iron 2, which is iron 2 plus, and iron 3, which is iron 3 plus. Okay, so those are on your table for you there. So for the ones in the middle, you can kind of look them up. Even if I give you one that is not on here, so who isn't on here? Let's say I gave you vanadium. Vanadium is not on this chart. Say I gave you vanadium 2O3. Could you tell me what the charge of the vanadium is? Yeah. It would be positive 3. And if you've forgotten why, you have 3 oxygens, and oxygen always has a charge of -2, which means you have a total of -6, which means that in order to balance that out, each of the 2 vanadiums has to be +3. So you could say, okay, that's vanadium 3. Okay? All right. But chances are you won't have to do that, and most of them are on here anyway. But let's just go back here and make sure that you know you're as easy as 1, 2, 3 bits. So we have 1, 2, 3, and then we skip the transit, most of the transition metals except for that very first column there. Aluminum, the group with boron and aluminum, is also +3, okay? And then carbon does not tend to form ions, okay? It tends to form covalent bonds, so they're sharing electrons instead. Do we know what charge we form in group 18? It's got a full valence shell, so does it want to gain or lose electrons? No, so it does not tend to form ions. How about group 17? It's going to be -1. It has 7 valence electrons. It wants 1 extra to form a full shell. So we have -1, and then group 16 would be -2, and 15 would be -3. And if any of you want to get really fancy, you can say silver is always +1. Zinc is always +2, and so is cadmium. And aluminum, gallium, and indium are always +3. And look, that's also as easy as 1, 2, 3. You don't need to memorize that, but it's kind of a nice little trick if you like it, okay? Those ones are not multivalent. They don't have different charges, okay? Silver is only ever +1. Zinc is only ever +2. But do you need to remember that? No, because if you go over here and you look under S for silver, does it have a Roman numeral? No, which means it's only ever +1, okay? All right, back to kinetics. There we go. So when aluminum gets together with chloride, what charge is aluminum? +3. What charge is chloride? -1. And so the compound form between them would be AlCl3. Would it be okay to write Cl3Al? No, we always write the metal first. The cation always comes first. And then we are left with who gets kicked out? Hydrogen. How are we going to write hydrogen? We're going to write it as H2 because it is one of the diatomic elements, okay? And if we needed to write the state, what state is hydrogen? It's a gas. We know that hydrogen is a gas. And we've just been doing this reaction in aqueous solution. This is aqueous hydrochloric acid. So what state do you think the aluminum chloride would be? Probably also aqueous. Okay? And if you want to double check, we're going to look again in your data booklet, and we are going to go to page 4. You may or may not have seen this last year, but it's a lovely little table that tells you when some compounds will dissolve and when they will not dissolve. So if we're looking for aluminum and chlorine together, normally we look up the negative ion first because it's on the left. So we look down our row of negative ions and we say, what's down here? Oh, there's chlorine. Okay, there's chlorine. And if chlorine is with silver plus, lead 2+, or copper 1+, we can go scroll across here, and that says low solubility. What does that mean? What does low solubility mean? It means that it does not dissolve well, which means that will it be aqueous or will it be a solid? It's going to be a solid, okay? But is aluminum in that list? No. So aluminum would fall in the all others category. And so when we put it together with chloride, it would be soluble. And what state is something if it's soluble? Aqueous. And don't worry, we'll spend a little bit more time with this chart so you get a little bit more familiar with it. But this is just a brief introduction here. Okay. So now we've gone through, we've come up with our reaction. That's fantastic. Can you think, by looking at this equation, what one good way of measuring the rate of this reaction would be? What could we measure here? We have solid aluminum, we have an acid, we have some aqueous ionic compound, and we have H2 gas. Tell your partner at least 3 different ways that you could measure the rate of this reaction.
We can do it by gas.
When you say by gas, what do you mean? Volume of the gas, yeah. Okay, what's one thing we could measure? The mass of the solid. So we could do the mass of the aluminum. So we could measure change in mass of the solid over the change in time. So if you are showing your calculation for a rate, you should always write rate equals, and then you should write delta whatever over delta time. Okay, that's going to be your first step, is to write the equation. That was not good. So you always write the equation if you're going to actually be calculating it. Okay? What is something else that we could measure? We could do concentration over time for who? Aqueous things. Now, who would be a good thing to measure concentration over time? The HCl, because HCl contains acids. So we could do the change in the concentration of who? H plus over the change in time, because H plus is measured by pH, okay? We could also measure, so that's our second way. And I'm running out of room, so I'm not going to write rate equals, but you should write rate equals, okay? What's our third way that we could measure? What else could we measure? Sorry? We could measure the overall mass. Sorry? Oh, the volume. We could measure the volume, yes. Okay, so we could measure the change in the volume of what? What are we measuring the volume of? Hydrogen. Volume of H2 over the change in time. So that's 3 ways that we could measure the rate. There's actually a 4th and a 5th way as well. This reaction is great. There's so many different ways to measure the rate. One of the other ways to do it, let's just see if we can find it here. Nope, not that one. Nope, not that one. Okay. Just let me find it and then I'll tell you what page it's on. Gas. Here we go. So this is on page 24. Not only can we measure volume for a gas, but what else can you measure about a gas? Page 24. You can measure volume of a gas. You can also measure the pressure of a gas. And what do you use to measure pressure? You use a pressure gauge. All right. And there are ones that just look like that. So if you were to have your reaction here, here's your solid, and we get the little bubbles coming up, and the bubbles continue on through here, and the bubbles push down, and usually this is mercury. Okay, they'll push down on it, and what that does is that pushes the other end up, and that lets you know what the pressure is. You literally measure the distance, and you'll measure your pressure in millimeters of mercury. It's literally the number of millimeters of mercury that gets pushed up by. You don't have to worry about the details of that. You just have to say we could measure pressure of a gas with a pressure gauge. Okay? The only problem is, what if I had it like this? Oh, I didn't leave a little hole for the thing. What if I had like this? Okay, and then it went off to the other thing. Okay, so the rest of this is the same as the other one. Okay, it's all this business over here. What's the problem with the way I have drawn it? There's no lid. So what would happen with the gas? It would just escape. So if you are going to measure pressure, can you use an open system? No, pressure will not work if you have an open system. Pressure will only work if you have a closed system. Do you guys know what I mean when I say system? It's just a scientific chemical term meaning the stuff we are looking at, the reaction that we are looking at. That is called the system, okay? So you can only measure the pressure if the system is closed. The open system won't work. Is good? Okay. When we're measuring volume, is that a closed system or an open system? It's also a closed system. You can only measure volume if you use a closed system. So that's one of the things that you can be asked. You can say, you know, how could you measure it? What conditions would be necessary? So you might, if you're going to choose volume or pressure, you would need to specify that it is a closed system, okay? If you're going to measure pH, does it matter if there's a lid on it or not? No, if you're not measuring a gas, it doesn't matter whether you have a lid or not. Nothing is escaping because it's just dissolved in the water and it's not going to leave, okay? I want you to think now, is there another way that we could measure the hydrogen? And it has nothing to do with volume and it has nothing to do with pressure. Imagine that you've got this flask. Yeah, we could do mass. Because what could we do? We could just throw this thing on a balance. Yeah? And as the gas escapes, what will happen to the mass? As the gas escapes, the mass will decrease. And I think if you don't want to draw this, I think we have this on page. Let's find the page. Oh, here we go. It's on the next page. Okay, here we have something burning, but it's the same idea. If a gas is produced, so maybe I will draw it here. So the mass decreases as the gas escapes. What kind of a system do you need for this to work? You must have an open system. Is good? Okay. Now, in order to do the next little bit, we really want to know about ionic reactions. But I feel like we need a stand up and stretch break. So we're all going to stand up. And we're all going to stretch. We're going to turn on the lights. I'm just going to wake you up. Everybody stand. I'm going to stand here on this thing. Y'all see me. And what we're going to do is we're going to stretch our arms out to the side and then kind of like backward, because, you know, we always are hunched over like this. So we kind of want to like, oh, and you can put your head back too. That's kind of nice. Oh, and then we're going to go like this and go like this and go like this. The reason that we are touching the left side of our body with our right hand and the right side of our body with our left hand is it actually makes the two hemispheres of our brain connect better with each other. And now we're going to do it in front just to mix things up a little bit. Okay. And now we're going to, if you can, without hitting yourself or anybody else, we're going to just do a little bit of this because it just feels good. Okay. And we're going to drop our head to one side and then roll it down to our chest and then drop it to the other side and then back. And we're going to go the other way. And now you can just do some slow head circles. And when you've done a couple, you can start going the other way. Shake your arms out. Jump up and down 3 times. Keep jumping. Keep jumping. Okay. All right. Back to business. With my grade 9, I would actually send them out to run around the parking lot, but we don't have time for that. So, all right. So we are actually going to bop now over to our ionic reactions, unit 0, because we want to look at using the solubility chart. So this is on page 15 in your unit 0. Page 15 in unit 0. Remind your partner what it means if it says soluble.
Meltable.
Does it mean meltable? Dissolvable. Soluble is dissolvable. Okay, so you also have your pink version of this chart on page 4, so you don't always have to be flipping back to this page. Okay, low solubility means not dissolvable. Or actually not very dissolvable. We actually have a whole unit devoted to compounds that only dissolve like, and when I say I mean like 10 to the negative 6 molar or 10 to the negative 20 molar. Okay, so like 0.00000000001 molar. It will dissolve, but only that much. Okay, but that's unit 3, so we won't worry about that yet. All right, so here we have our little chart. Soluble, it will dissolve in water. It will become aqueous. Low solubility, it will not dissolve in water. It will be a solid. So this is on the next page now. We are going to predict the states. So I would like you to look on your chart and let's predict the state of BaSO4. Yes?
To be soluble, is water the only thing that it can dissolve in?
It's the only thing that we're concerned about because what they actually call water the universal solvent because it dissolves most things. The times when we would need something other than water is if we have a substance which is not ionic and which is non-polar, because only polar things will dissolve in a polar solvent, like water. Water is a polar solvent. And in grade 12, we don't deal with those much at all. So yeah, we'll only be dealing with water as a solvent this year. Good question. So you're going to go look up the anion on the chart. You're going to look up sulfate and say, oh, there's sulfate. Excellent. And here is barium. And what does it say? Low solubility. All right. What does that mean? That means it would be a solid. Excellent. Now, what if we have AlOH3? Who do you look up first? You look up the OH, and then you look and you say, is aluminum over here? Is it in my list? No. Therefore, it falls in the category all others. Okay, so if it's not in the list, it falls in the category all others. So that's Al3+. Now, I do have to tell you that although I have listed out all the alkali ions here, your pink booklet does not list them. If we go look at that page, it just says alkali ions. So that means that you need to know where your alkali ions are on your periodic table. Where are your alkali ions? They are group number 1. So that would be right here. Okay, so these are your alkali ions. Now, what if you don't want to flip to the periodic table to look and see, is rubidium an alkali ion? Yes, it is. Is strontium? No, it's not. But what if you don't want to flip back and forth and look? We can do it another way because on our solubility chart, right up at the very tippy top, it does list them. Okay, so you don't actually have to look anywhere. It only lists them the once. Okay, and every other time it says alkali ions, you just have to look up at the top of the page. Okay? And the other thing to remember is that alkali ions are soluble with everything all the time. Okay? Alkali ions with everything are always soluble. Okay, so it's quite an easy rule to remember. Okay? All right, back to here. All right, so we had aluminum, hydroxide. That is low solubility. So what state would it be? Solid. Okay. Now this one, we have CuCl2. Now we look up the anion, chloride. Now we have a little issue here. I have copper listed down in the low solubility area. However, this one is only copper plus. Okay, so this is copper 1. Which copper is this? Copper 2. How do we know that it's 2 plus? Because we've got the Cl, we have 2 of them. Yes? So you have to watch out for that. It's the only one that does that, okay, where it lists the copper and you might get tricked by it. Okay, all the rest of them are just more straightforward, okay? So copper 2 plus is up here in all others, and therefore it is soluble. So this would be aqueous. All right. It can be very useful to memorize that all salts containing ammonium, the alkali ions, and nitrate are all soluble. Acetate isn't as important. I will put it in brackets. Okay? But it's useful, but do you need to memorize it? Not really, because guess what? On your data pages, look what it says. Oh, all my alkali ions are soluble. All my ammonium ions are soluble with all cations. All of my nitrates and acetates are soluble. Okay? The reason I didn't get wound up about hydrogen is hydrogen does its own weird thing that we'll learn about in acids and bases. Okay? So one of the things you're going to do for homework tonight is to write the state for these, but we're not going to do that right now. We are going to move on to precipitation reactions. Okay? And because I'm not going to run to the back room and get it, we're going to watch this little video here. Okay?
For this example, we will predict the products, balance the chemical equation.
No, we're not going to do that, actually. To be honest, no, we're not. Okay. Do you see how here, and I might get this out next day, but I didn't have time today and we've only got 10 minutes left, so I'll grab it for next day. Do you see how we have a clear colorless solution here? And up here we have another clear colorless solution, yes? But when we pour the two together, what happens? It's yellow, and it's not only yellow. Is it clear? No. It's yellow. We have a yellow solid. You can tell it is a solid because it reflects the light. It is opaque. If you see something opaque or cloudy, that tells you have a solid. So unless it is clear, if it's clear, that means you have something which is soluble and aqueous because it has dissociated into all the little ions. And ions are so small that they don't scatter light. But the particles of a solid, I mean, they are little tiny chunks of solid. They're so small that it's hard to see the individual little particles. However, they are big enough to scatter light. Okay, so solid particles are big enough to scatter light. Individual ions are not big enough to scatter the light. Solid particles, big enough to scatter light. Therefore, it will be opaque. individual ions. Are too small to scatter light. Therefore, it will be transparent. Okay, so just to bop back here for a moment, where did it go? There we are. So if we were to look at, and you don't have to go back here because we looked at this last day, but if you see this, is this going to be transparent or is this going to be cloudy? These are individual ions. It's going to be transparent. I know they look enormous, but that's just because we had to draw like letters inside them. They're actually like so small you cannot even see them with a microscope, okay? Whereas if we actually had a little crystal that contained this many ions, we might be able to see it with a microscope. Probably we would need a few more than that, but you'd be able to see a little crystal with a microscope. Ions, though, too small, won't scatter the light. Okay. Does anybody remember what that solid is called? A solid that forms when you mix two solutions together. That is called a precipitate. You know what? Why am I writing it down? I don't know. It's right here. Precipitate. I often do that. I've written it down. It is a solid that forms during a double replacement reaction. Okay. And we can abbreviate it PPT. Okay. Okay. So let's take a look at what a reaction like this looks like. Here we have, is this a suspension where we have solid particles, or is this a solution where everything is dissolved and it's going to be clear? This is going to be clear because it's individual ions, and it is a solution, which is why we see the little subscript here, aqueous. It is completely dissolved. It has, what have the ions done? They have dissociated. Yes. And if you remember, sodium is an alkali ion, and alkaline ions are what? Soluble with what? They're soluble when you put them with what ions? All of them. All of them. Alkali ions are soluble with everything else. So you could put it with chloride, you could put it with nitrate, sulfate, phosphate, any anion you want, and it will dissociate into ions. Nitrate is another one that is soluble with everything. Okay? Nitrate, NO3 minus, is soluble with everything. Okay? So, if it is soluble with everything, that means it dissolves, which means that the ions break apart. In other words, the ions break apart. In other words, they dissociate. Will this be cloudy or clear? This will be clear. Okay? Now, when we mix these two together, we pour them into a beaker together. If we go and we look up chloride and silver on our data table, here's chloride, here's silver, and silver is, with chloride is, it's low solubility, it is a solid. Okay, silver with chloride, low solubility, it is a solid. So we go back here and we say, oh my gosh, look what we have formed. We have formed a PPT, a precipitate. In other words, a solid. To be honest with you, it's not going to look like that. It's not going to be a chunk at the bottom. It's going to look like cloudy stuff. Yes? But because we're drawing particles and we don't want to spend all day, we're just going to show it like that. Okay? But what's happening with the sodiums and the nitrates? Remember, sodium is an alkali, it's soluble with everything. Nitrate is soluble with everything. So what do? They just stay floating around. Yes? So, if we were to, here's our reaction here. We have sodium chloride aqueous plus AgNO3 aqueous gives NaNO3 aqueous plus silver chloride solid. Anyone remember writing a complete ionic equation last year? When we write a complete ionic equation, if you didn't do it last year, it's fine, it's no big deal. Anytime you have an aqueous compound, you separate the ions because in an aqueous compound, the ions are separate. Yes? So we're going to take our NaCl and instead of writing it together, NaCl aqueous, we're going to write it as Na plus aqueous plus Cl minus aqueous. Now, we also have silver nitrate, which is also aqueous. Because it is aqueous, what does that mean? The ions are actually separate. Yes? So we're going to write it instead of AgNO3 all together. What are we going to write? Ag plus NO3 minus, and those are both aqueous. So what we're doing is we're really showing what's actually in the beakers, right? We're taking what we see up here and just writing it down here. We're taking what we see up here and writing it down here. And then finally, we get over to the other side. How about the NaNO3? Is it together or is it apart? NaNO3 aqueous. It's apart. It is dissociated. So we're going to write Na plus NO3 minus aqueous. And then what about our silver chloride? Is the silver chloride together or is it apart? It is together. So when you have a solid, you're going to write it as AgCl solid. You write it together. And that's how you write a complete ionic equation. Okay? Now, we have like 1 minute left. So would it be okay with you if I just posted the homework on Teams?
Yep.
Okay, so I'm going to post it on Teams. You must check there and make sure you get it. Okay? I'll figure out what it is in just a moment. Hi.
I have a question.
Yes.
Oh, I'll do the homework. Right? I'm just
Uh-huh.
saying,
Yeah. Perfect.
I don't know. This question, I feel like the answer is wrong.
The answer could be wrong. It's entirely possible because this looks good, what you've done. Yeah. So that is this one. 14.
You said AG plus this, and I have the
Oh,
two.
it should have a 2 there. Yes, definitely. Okay, thank you so much.
I was like really panicking. Yeah.
Okay, why? I need a 2 AG plus. Thank you so much.
Thank you.
Yes.
See you.
I don't. No. It's okay. It's okay. Page 6.
I'm dying, girl. I'm grinding it, but I'm dying. People talk to you up.
0.030. Thank you. Yes, and your question. Oh.
Bro, I have freaking. Freaking dying. On how this.
Although it is helpful to understand laws. Yeah. That's your. Okay. Yeah. Hi, how are you? I'm good. It's tiring teaching 10-12 twice in a row in the afternoon. Because all I do is talk. Talk. And but it's okay. What's that? Well, thank you. Oh. All right. I'm gonna have a water. God bless you, Mrs. Friends. For the brand. Right? It is good, right? I know, we just do that every day. So if I want to do a quarter past and if we're on, we break. Oh my God, that's so good.
Thank you.
Ready to go Monday.
See you tomorrow.
See you tomorrow. Hasta mañana.
Hasta mañana.